Hi, and welcome to the 38th day of Just Start Programming, the Rust programming language. Today we will look into one of the advanced topics in Rust, which is something I am really looking forward to learn, as we have seen several macros being used in the sample code snippets, and up to until now it is a kind of a black box and mysterious. Join me live in one take, no shortcuts, no secrets. So let's just start programming. All right, so here we are. The other day, I think we covered advanced functions and closures. So today we'll cover macros. But before that, let's backtrack a little bit just to refresh our memory. So, what do we have here? Yeah, function pointers, just like in other programming languages. Okay, function pointers. So we have this function do twice, takes two parameters. Okay, maybe let's analyze the code snippet itself. So add one and do twice, where do twice, the parameter is a function that accepts I32 and returns I32. And then here you have another argument. And finally, this will return I32. So the syntax is something new. Okay, we haven't seen this before. Here you have f argument plus f argument. And then here you have answer do twice. So the function being passed is actually add one. Yeah, here. It seems like it doesn't require any references, but here it's just being passed directly, as this one doesn't take in any references as well. And then x plus 1, so whatever the value in add 1. Okay, so where does this come from? Mm, 5 is here. How did it become 12? I think the other day we might have done some analysis here. Let's go through once again. So assuming 5 is being passed here, it becomes 6. So it returns 6. Okay, the function is here and arg is here. So arg is being passed to the function. So 5, this 5 goes here. inside this one, which is this, becomes 6. So once again, this one is passed here. 5 plus 1, it becomes 6, and then this is being returned, which is also an I32. So that's why 12 is the answer. Okay. So it's unlike closures. Fn is a type rather than a trait. So it's a type. You can see here, f is the variable and this is the type. What else is here? Vect. Oh, okay. As an example of where you could use either a closure defined inline or a name function, let's look at a use of map method provided by the iterator. To use the map method to turn a vector of numbers into a vector of strings, we could use a closure. So we start off with vector, so vector macro, and then here a vector of string. So the numbers are going to be converted into a vector of strings. So from here, list of numbers, there's an iterator, then map, then you have the closure, which is I, which is the integer I32 here. So I32 is converted to a string using this function and then returns a new collection. Or we could name a function as the argument to a map instead of the closure. So here, once you have the map, so there's this difference where you have a closure. In this case, it's a module, toString. Okay, so using string toString method to convert numbers to string. 20-30. Okay, so it uses toString method. Okay, so toString is a function, so it's being passed here. So there's a little bit of magic going on here. Note that we must use the fully qualified syntax talked about in advanced traits because there are multiple functions available named toString. Yeah, so we need to refer to toString colon toString colon toString. So fully qualified syntax. Here we're using toString function defined in the toString trait, which the standard library has implemented for any type that implements display. Okay. Here, returning closures. Closures are represented by traits, which means you can't return closures directly. So, in most cases where you might want to return a trait, you can instead use a concrete type that implements trait as the return value of the function. However, you can usually do that with closures because they don't have a concrete type that is returnable. You're not allowed to use function pointer as a return type if the closure captures any values from its scope. For example, instead you would normally use IMPL trait syntax we learned in chapter 10. You could return any function type using fn, fn1, fnmod. For example, in 20-32, okay, this one returns a closure. Okay, so the return is an implementation of fn I32. Okay, then here you have xx plus 1. So this will be returned. as an function I32. However, as we noted in closure type, inference, and annotation, each closure is also its own distinct type. If you need to work with multiple functions, you have the same signature but different implementation. You will need to use a trait object for them. Consider what happens if you write a code like that is shown in listing 20-33. Okay, so this won't compile. What's in here? Okay, so main code, you have a vector macro where it contains closure, then another closure. Okay, returns closure, returns an implementation of fn32, which looks like this, and this one. Okay, so here the parameter is I32, but it returns IMPL, implementation of function I32. Then you have a move. Okay, so why it will not compile? Here we have two functions, returns closure and returns initialize closure, which both return, okay, the same thing. Notice that the closures that they return are different, even though they implement the same type. If we try to compile this, Rust lets us know that it won't work. Okay, so what's the issue here? Expected opaque type found a different opaque type. Mismatch types. It says mismatch types. They almost look the same. FN I32. Yeah, they look the same. So what is wrong? The error message tells us that whenever we return IMPL trait, Rust creates a unique opaque type. A type where we cannot see into the details of what Rust constructs for us. So even though these functions both return closures that implement the same trait, the opaque types Rust generates for each are distinct. This is similar to how Rust produces different concrete types for distinct async block, even when they have the same output type, as we saw in working with any number of features. We have seen a solution to this problem a few times. Now we can use a trait object as in listing. Okay, so yeah, so just like in I think in this chapter the same solution was used. So you wrap it with box, but then this one is dynamic, so now they will look exactly the same type when they are being returned. Yeah, this code will compile just fine. For more about trait objects, refer to the section using trait objects that allow for values of different types. So that was chapter 18. So how far we have gone since day 1. We're almost at the finish line. So for those who accompanied me in this journey, thank you so much. And let's move on to the next topic, which is macros. Yeah. Macros. We've used macros like printline. This is the first macro we have used throughout this book, but we haven't fully explored what macro is and how it works. Yeah, I think after some time from printline, I realized that debug dbg macro is more useful. Anyway, that's the purpose why we are printing values It's mainly to see, so debug is more useful. Okay, the term macro refers to a family of features in Rust. Declarative macros with macro rules. And three kinds of procedural macros. Custom derived macros that specify code added with the derived attribute used on structs and enums. Yep, so we have seen this several times. Derived debug. Attribute-like macros that define custom attributes usable on any item. And this one I'm not sure yet. And function-like macros that look like function calls but operate on the token specified as their argument. We have seen this in vector. So you have the vect exclamation mark. We'll talk about each of these in turn, but first let's look at why we even need macros. Why do we need macros when we already have functions? The difference between macros and functions, fundamentally, macros are a way of writing code that writes other code, which is known as meta-programming. In Appendix C, okay, derived couple traits, we discuss derive attribute, which generates an implementation of various traits for you. We've also used println and vect macros throughout the book. All of these macros expand to produce more code than the code you've written manually. More code, so it's being expanded. Metaprogramming is useful for reducing the amount of code you have to write and maintain, which is also one of the roles of functions. However, macros have some additional powers that functions don't have. A function signature must declare the number and type of parameters the function has. Macros, on the other hand, can take a variable number of parameters. Okay, so that's the difference. Or it could be, there could be a way for a function as well. Anyway, the topic is macros. We can call println hello with one argument, or println hello is name with two arguments. Also, macros are expanded before the compiler interprets the meaning of a code. So a macro can, for example, implement a trait on a given type. A function can't. What was that again? Okay, so they are expanded before a compiler interprets the meaning of the code. Implement a trait on a given type. A function can, because it gets called at runtime and a trait needs to be implemented at compile time. The downside of implementing a macro instead of a function is that macro definitions are more complex than function definitions because you're writing Rust code that writes Rust code. That's interesting. You're writing Rust code that writes Rust code. Due to this indirection, macro definitions are generally more difficult to read, understand, and maintain than function definitions. Yeah, so there's a big mystery behind this, and also vect debug. Don't know what's going on there. Another important difference between macros and function is that you must define macros or bring them into scope before you call them in a file. As opposed to functions, you can define anywhere and call anywhere. Yeah, so this is true. Functions you can define anywhere and call anywhere. But for macros, you define macros or bring them into scope before you call them in a file. My guess is this could be like this one. Okay, but we'll see. Declarative macros with macro rules for general meta programming. Okay, the most widely used form of macros in Rust is declarative macro. These are also sometimes referred to as macros by type, macro rules, macros, or just plain macros. At their core, declarative macros allow you to write something similar to Rust match expression. Okay, so it's like a Rust match expression. As discussed in Chapter 6, match expressions are control structures that take an expression, compare the resultant value of the expression to patterns, and then run the code associated with the matching pattern. Macros also compare value to patterns that are associated with particular code. In this situation, the value is the literal Rust source code passed to the macro. Okay. The patterns are compared with the structure of that source code. And the code associated with each pattern, when matched, replaces the code passed to the macro. This all happens during compilation. So it sounds really complex. So they compare a value to patterns. Literal Rust source code passed to the macro. And the patterns are compared with the structure of that source code. And the code associated with each pattern when matched replaces the code passed to the macro. It's quite a long process. To define a macro, you use the macro rules construct. Let's explore how to use macro rules by looking at how vec macro is defined. Chapter 8 covers how we can use the vec macro to create a new vector with particular values. For example, the following macro creates a new vector containing 3 integers. Okay, 3 integers vector. We could also use the vec macro to make a vector of 2 integers or a vector of 5 string slices. We wouldn't be able to use a function. Okay, we wouldn't be able to use a function to do the same because we wouldn't know the number or type of values up front. That's correct. But for macro, it's more dynamic. So it's either integers or string. You can do that. Okay, so 20-35 shows a slightly simplified definition of the vec macro. Okay, so let's take note of a few things. So you have this macro export, then macro rules. Oh, even macro rules is a macro also. Then vec. Then what is this? This looks strange. I don't know how to interpret this. Totally new. Okay. Let mut. Okay, so it's a mutable variable where vector with a new constructor. Okay, then here again is something new. All right, so we don't understand this. Okay, note the actual definition of vec macro in standard library includes code to pre-allocate the correct amount of memory up front. That code is an optimization that we don't include here. To make the example simpler, The macro export annotation indicates that this macro should be made available whenever the crate in which the macro is defined is brought into scope. So that's explanation of macro export. Without this annotation, the macro can't be brought into scope. We then start the macro definition with macro rules and the name of the macro we are defining without the exclamation mark. Okay, so here vect is a macro, but since we are still defining it, there's no exclamation mark. The name in this case is vect, is followed by curly brackets denoting the body of the macro definition. The structure in vect macro body is similar to the structure of a match expression. Here we have one arm with the pattern. Okay, so it's a pattern. Yeah, so just like match, and then you have the arm pattern. Okay, so what's the pattern here? How do we interpret the pattern? Followed by this one, and then the block of code associated with this pattern. If the pattern matches, the associated block of code will be emitted. Given that this is the only pattern in this macro, there is only one valid way to match. Any other pattern will result in an error. More complex macros will have more than one arm. Okay, so you need to understand what this is. Valid pattern syntax in macro definition is different from the pattern syntax covered in chapter 19 because macro patterns are matched against Rust code structure rather than values. Okay, so this one we're matching it against Rust code structure. Let's walk through the pattern pieces in 20-29. 20-29. Mean for full macro pattern syntax. See Rust reference. Okay, macros by example. And this is our guide, cheat sheet. Okay, identifier, that's vec. What is this? Macro rules definition. Macro rules. Okay, so I don't understand this. Let's come back here. First, we use a set of parentheses to encompass the whole pattern. Set of parentheses. We use a $sign to declare, okay, $sign to declare a variable in the macro system that will contain the Rust code matching the pattern. $sign makes it clear that these macro variables as opposed to a regular Rust variable. Okay, so it's to distinguish regular Rust variable versus macro variable. Next comes a set of parentheses. So maybe this one and this one. That captures values that match the pattern within the parentheses for use in the replacement code. Within this is, okay, $x expr, which matches any Rust expression and gives the expression the name. Matches any Rust expression, maybe this, and gives the expression the name $x. Match and give a name. The comma following this indicates a literal comma separator. Character must appear between each instance of the code that matches the code with this. Okay, so that would look like probably this, you're referring to the comma. Okay, let's see. The star or asterisk star specifies that the pattern matches 0 or more of whatever precedes this. Okay, 0 or more of, okay, the comma is here, then 0 or more. Okay. When we call this macro with vect123, the $x pattern matches 3 times with the 3 expressions 1, 2, and 3. Okay, so this one is the expression 1, 2, and 3. Now look at the pattern in the body of the code associated with temp-vec.push within this temp-vec.push. Okay, temp-vec.push. Okay. The $x is replaced with each expression match. When we call this macro with vec123, the code generated that replaces this macro will be the following. Okay, so it will replace this. It will be expanded to temp-vec, vec-new, temp-vec push 1, 2, 3, and temp-vec. We have defined a macro that can take any number of arguments of any type and can generate code to create a vector containing the specified elements. To learn more about how to write macros, consult the online documentation and other resources. Oh my, so there's another book here, the Little Book of Rust Macros. Okay, first you have a cheat sheet and then now you have another book. Great. Started by Danielle Keep and continued by Lucas Worth. Yeah. Let's see how we can cover this later also. Let's continue with this for the time being. Procedural macros for generating code from attributes. The second form of macros is the procedural macro. Okay, so this is declarative macro so far. The other one is procedural, which acts more like a function and is a type of procedure. Procedural macros accept some code as an input, operate on that code, and produce some code as an output, rather than matching against patterns and replacing the code with other codes as declarative macros do. Okay, so this is sounding more like a function. Yeah, acts more like a function. The 3 kinds of procedural macros are custom derived, attribute-like, and function-like, and all work in a similar fashion. When creating procedural macros, the definitions must reside in their own crate with a special crate type. This is for complex technical reasons that we hope to eliminate in the future. Listing 20-36, we show how to define a procedural macro where some attribute is a placeholder for using a specific macro variety. So it's like this. Okay, macro custom derived attribute, then some name input, token stream. Okay, the function that defines a procedural macro takes a token stream as an input and produces a token stream as an output. The token stream type is defined by proc macro crate that is included with Rust and represents a sequence of tokens. This is the core of macro. The source code that macro is operating on makes up the input token stream. And the code the macro produces is the output token stream. The function also has an attribute attached to it that specifies which kind of procedural macro we're creating. We can have multiple kinds of procedural macros in the same crate. Let's look at the different kinds of procedural macros. We'll start with custom derived macro and then explain the small dissimilarities that make the other forms different. How to write a custom derived macro. Let's create a crate named hello macro. Okay, so let's do this. Finally. Um, create new, no, not create, cargo new. Hello macro. I think this is the one from the other day. We can close this. Hello world. Okay. Okay, you can build. Let's come back here. Okay, hello macro that defines a trait named hello macro with one associated function named hello macro. Rather than making our users implement the hello macro trait for each of their types, we'll provide a procedural macro so users can annotate their type with sharp derive hello macro to get a default implementation of the hello macro function. The default implementation will print hello macro, my name is type name. The type name is the name of the type on which this trait has been defined. In other words, we'll write a crate that enables another programmer to write a code like listing 20-37. Crate. Okay, so this will not compile, but let's just copy it. Okay. This code will print hello macro by name. My name is pancakes when we're done. The first step is to make a new library crate like this. Okay. Can we do that? Macro already exists. Okay. Just create a new file. lib.rs. Then lib.rs, we copy this one. Pub trait hello macro. The macro is already here. What else is missing? We have a trait and its function at this point are create user could implement a trait to achieve the desired functionality. 20-39. Pancakes. Struct pancakes. Pancakes. Hello macro. Pancakes. Hello macro. Hello macro for pancakes. Let's remove this for now. So it will look like. I don't need to. Hello macro. My name is pancakes. Okay. Because we have trait hello macro with the hello macro function. Okay, then we are implementing the trait for pancakes, where hello macro is implemented, then it will print this, so that once you have pancakes, you call hello macro, this is implemented. Okay, so that is clear. Okay, what is this? The next step is to define the procedural macro. At the time of this writing, procedural macros need to be in their own crate. So eventually this restriction might be lifted. The convention for structuring crates and macro crate is as follows. For a crate named foo, a custom derived procedural macro crate is called foo derived. Okay, so that's the naming convention here. Okay, so I just copy this. So it's a new crate package and here. Okay, so maybe if we go into hello macro derived and we open up another Visual Studio Code. Yeah, we will close Copilot, we will close this. Okay, and let's come back. Our two crates are tightly related, so we create the procedural macro crate within the directory of, wait, I think we did something wrong. We create the procedural macro crate within the directory of our hello macro crate. So it's wrong. We can move that one. So mv hello macro derive to hello macro. What I'm seeing here, hello macro derive. Okay, so let's see if this is correct. Refresh this. So we have hello macro derive here. Okay. If we change the trait definition in hello macro, we'll have to change the implementation of the procedural macro in hello macro derive as well. The two crates will need to be published separately, and programmers using these crates will need to add both as dependencies and bring them into scope. Could instead have the hello macro crate use hello macro derive as dependency and re-export the procedural macro code. However, the way we've structured the project, it makes project makes it possible for programmers to use hello macro even if they don't want the derived functionality. You need to declare the hello macro derived crate as a procedural macro crate. You also need functionality from scene and quote crates, as you'll see in a moment. So we need to add them as dependencies. Add the following to the cargo toml for hello macro derived. Okay, so let's this hello macro derived cargo toml. Okay. Can remove these dependencies. Okay. To start defining the procedural macro, place the code in 20-40 to your source librs file for hello macro derived crate. 20-40. Okay, so we copy this. Source librs. Note that this code won't compile until we added a definition for impl hello macro function. Source librs. And let me put that in here. What will that compile? Hello macro derived source librs. Hello macro derived source librs. Yeah, correct. Seems to be fine. Notice that we have split the code into hello macro derived function, which is responsible for parsing the token stream, and the impl hello macro function. Okay, impl hello macro function, which is responsible for transforming the syntax tree. This makes writing a procedural macro more convenient. Syntax tree. The code in the outer function hello macro derive in this case will be the same for almost every procedural macro crate you see or crate. Okay, so this one, this integer. The code you specify in the body of the inner function impl hello macro in this case will be different depending on your procedural macro's purpose. We've introduced 3 new crates: proc macro, scene, and quote. The proc macro crate comes with Rust, so we didn't need to add that to the dependencies in cargo.toml. The proc macro crate is the compiler's API that allows us to read and manipulate Rust code from our code. The scene crate parses Rust code from string into a data structure that we can perform operations on. The code crate turns scene data structure back into Rust code. Okay, so scene crate parses Rust code. Okay, so scene is from string into a data structure, and code turns scene data structure back into Rust code. These crates make it much simpler to parse any sort of Rust code we might want to handle. Writing a full parser for Rust code is no simple task. Yes, indeed, it's not a simple task. The hello macro derived function will be called when a user of our library specifies sharp derived hello macro. Okay, so from here, sharp derived hello macro. Comment it out. Unresolved. Okay, add it to your cargo toml. This one. How do we add it? Hello macro derived. .0.0. Right. Right. Oh, 0.1.0. Okay. Okay. So hello derived function here with proc macro derived and specified name hello macro, which matches our trait name. This is the convention most procedural macros follow. Let's inspect it a little bit. No macro. Okay, so they look the same. Okay, so now it jumps to what is this? No. Oh, okay, so this looks like a generated code, it seems. Okay, let's continue. The hello macro derived function first converts the input from a token stream to a data structure that we can then interpret and perform operations on. This is where SYN comes into play. The parse function in SYN takes a token string and returns a derived input structure representing parse Rust code. Okay, so in 20-41 shows the relevant parts of the derived input struct we get from parsing struct pancakes string. The fields of this struct show that Rust code we parse is a unit struct with identifier meaning the name of pancakes. There are more fields on this struct for describing all sorts of Rust code. Check the SYN documentation for derived input for more information. Okay, struct derived input. Soon we'll define the IMPL hello macro function, which is where we'll build the new Rust code we want to include. But before we do, note that the output of our derived macro is also a token stream. The return token stream is added to the code that our crate users write. So when they compile their crate, they'll get the extra functionality that we provide in the modified token stream. You might have noticed that we're calling unwrap to cause the hello macro derived function to panic if we call SYN parse. Unwrap. It's necessary for our procedural macro to panic on errors because proc macro derived functions must return token stream rather than result to conform to the procedural macro API. Okay. So it should return token stream. We've simplified this example by using unwrap. In production code, you should provide more specific error messages about what went wrong by using panic or expect. So, and this is in the error handling chapter. Note that we have the code to turn the annotated Rust code from token stream into a derived input instance. Let's generate the code that implements the hello macro trait on the annotated type as shown in 20 42. Okay, so this one is in the derived source lib as copy source lib. And we'll add it here. Okay. So what does it do? We get an ident struct. Instance. Ident. Containing the name identifier. Okay, IST is here, which is a reference to scene derived input. Ident. Containing the name identifier of the annotated type using AST ident. The struct in 20-33 shows that when we run the impl hello macro function on the code listing in 20-31, so 20-31. What? Mm, 20-31, where is this? The ident we get will have the ident field with a value of pancakes. Thus, the name variable in string 20-34 will contain an ident struct instance that when printed will be string pancakes. The name of the struct in listing 20-37. Saying something about if we run the impl hello macro function, this one, the ident we get will have the ident field of the value of pancakes. Okay, so it was saying this one will have a value of pancakes. Thus, the name variable in listing 20-34 will contain an ident struct instance that when printed will be string pancakes. The quote macro, here's the quote macro. Listen, quote macro. Also provides some very cool templating mechanics we can enter. A sharp name and quote macro will replace it with the value in the variable name. Sharp name replace with the value in the variable name. Okay, so sharp name. Okay, so this was pancakes. So hello world for pancakes. Stringify pancakes. I think that's the output. Macro my name is. Okay. The stringify macro used here is built into Rust. It takes Rust expression 1 plus 2 and at compile time turns its expression into a string literal such as 1 plus 2. This is different from format or printline macros which evaluate the expression and then they turn their okay, so combine the expression which evaluate the expression then turn the result into a string. Okay, so it's a string literal. Okay, there's a possibility that the sharp name input might be an expression to print literally, so we use stringify
Using stringify also saves allocation by converting name to a string literal at compile time. At this point, cargo build should complete successfully both hello macro and hello macro derived. Let's hook up these crates to the code in 20-31 to see the procedural macro in action. Create a new binary project in your projects directory using, cargo new pancakes. In your projects, we need to add hello macro and hello macro derive as dependency to the pancakes crates cargo toml. If you're publishing your version of hello macro and hello macro derived to crates.ito, they will be regular dependencies. If not, you can specify them as path dependencies as follows. Okay. So we need to open up another one. Create a new one. Cargo new pancakes. Cakes. So first we need to add the dependencies. What was that? Okay. Put the code in main rs. Which code? Which code are we talking about? 20-37. Cargo run, okay. And add it here. Hello, macro, my name is Pancakes. Okay, but what happened to... okay, so actually we don't need this. Because the code is being used here in Pancakes. Okay, so derive hello macro from here, Pancakes hello macro. Okay. Attribute like macros. Oh, this is derive macros. So next, let's explore how other kinds of procedural macros differ from custom derived macros. Okay. Attribute like macros are similar to custom derived macros, but instead of generating code for the derived attribute, they allow you to create new attributes. They're also more flexible. Derive only works for structs and enums. Attributes can be applied to other items as well, such as functions. Here's an example of using an attribute-like macro. So you have an attribute named route that annotates functions when using a web application framework. Okay, so annotation where you have route, get HTTP method from slash. Okay, and then you have function index. This route attribute would be defined by the framework as procedural macro. The signature of the macro's definition function would look like this. Proc macro attribute route attribute token stream item token stream returns token stream. Here we have two parameters of type token stream. The first is for the contents of the attribute, the get and then the path part. The second is the body of the item the attribute is attached to. In this case, function index, and the rest of the function's body. Other than that, attribute like macros work the same way as custom derived macros. You create a crate with proc macro crate type and implement a function that generates the code you want. So they're saying they are similar, while here we're creating something like this. Let's come back to the code and try to see. Okay, so not that one. We have another one here. librs. So here we have proc macro derive. This one is proc macro attribute. Then you have the function hello macro derive input token stream impl help macro like this. Okay, then here it didn't say anything, just that you'll have this. So in this case it's hello macro derive. Yeah, so this one derive macro. So derive, okay, so this one follows a naming convention. However, this one for route get like this, you need to specify, okay, route something like this. Okay, so here we have two parameters of type token stream, this and this. The first is for the contents of the attribute, the get, okay, content of the attribute. The second part is the body of the item the attribute is attached to, in this case. Okay, so this one is for this and this one is for this. Other than that, attribute like macros work the same way as custom derived macros. You create a crate with proc macro. So let's come back here. You have a crate proc macro set to true. And implement a function that generates the code you want. Implement a function. Okay, so since we're talking about macro, this too is required. And implements a function. Okay, so this is the function that implements. So I assume it's still the same. whatever you want to do here, in this case hello macro print line, so this one is actually doing a print line. Wow. So just to do this, okay, so you define something like this. To do this is the ultimate implementation. So for a route, so the route will have something like this. Then you have another implementation. Okay, build the trait implementation. Do we have a trait implementation again? Because where's the trait? Pancakes. No, pancakes is a strong. Where's the trait again? Ah, the trait is here. Okay, hello macro. Implement hello macro. No, that one was hello macro. What's the implement? Okay, when we run the implement hello macro function, no, implementing the hello macro trait using the parse Rust code. Okay, so yeah, so this is the implementation. Why do we have it here again? We've split the code into hello macro derive, which is responsible for parsing, okay, and then the impl hello macro function, which is responsible for transforming the syntax tree. This makes, okay, so this one makes writing procedure macro more convenient. Okay, that's the only reason, just to break it up. Okay, so it will look something similar to this, except that this part here will have the route function signature for this one. Okay, it's really complex. Maybe once we read more into what was that here with Rust reference for macros and a little book of Rust macros, maybe I'll dedicate a few more days specifically for this after we finish the Rust book, the main Rust book, Rust lang book. So we're almost done. A few more. Final project, and we go through the appendix. All right. So what about function-like macros? Function-like macros define macros that look like function calls, similar to macro rules. I think this is the one that I really wanted. Okay. So they're more flexible than functions. For example, they can take a known number of arguments. However, macros can only be defined using the match-like syntax we discussed in declarative macros. Oh, I think that is the previous one. Not this, but the first one. Where is it? Declarative macros. Mm, Function like macros take a token stream parameter and their definition manipulates the token stream using Rust code as the other two types of procedural macros do. An example of a function like macro is an SQL. SQL macro that might be called like so. SQL. So there's a database, a select statement. Okay, this macro would parse SQL statement inside it and check that it's syntactically correct, which is much more complex processing than macro rules. Macro can do. The SQL macro would be defined like, okay, so this one is a proc macro SQL where you have the input, token stream, returns token string. This definition is similar to the custom derived macro signature. We receive the tokens that are inside the parentheses and return the code we wanted to generate. Oh, and then summary. Phew. Now you have some Rust features in your toolbox that you likely won't use often. Yeah, most likely. Not often, but you know they're available in a very particular circumstances. We've introduced several complex topics so that when you encounter them in error message suggestions or in other people's code, you'll be able to recognize these concepts and syntax. Use this chapter as a reference to guide you to solutions. Next, we'll put everything we've discussed throughout the book into practice and do one more project. Okay, so I would say it's just like scratching the surface so that at least when we see things like this, somehow underneath it there's an even more complex implementation. Yeah, we'll see in the actual projects later on. So yeah, so I'm excited to do this part together with you. If you're with me, uh, joining me in the stream, maybe tomorrow or the next day, we'll see. And we're almost near the finish line. So congratulations. So let me end here. So I ended a bit early today. Thanks for joining me. And let me thank my supporters and hope to see you in the next stream. Thank you so much.